Okay, so section 4.9, we're talking about the antiderivatives. We're going to look at number 12. So we're going to start working through some problems. Here they tell us g of x equals 11x to the 10th. What they're asking us to do is they're telling us to find the antiderivative of the following function. So, I mean, basically, if we want to write this in kind of like an integral formatting, they're asking us to take the integral of 11x to the 10th dx. Okay? Because once again, this was the derivative of the function. We want to go back to what the original function was. So if we remember back, we want to add 1 to the exponent. So we're going to take this x and we're going to add 1 to make that be 11. And then now remember we had 11 here. Now we're going to divide by what that new exponent was, in which then we get x to the 11th and then plus c. Now, if we were to think about taking the derivative of this function, we would take 11, multiply in front, so we'd have 11x to the 10th, and then the derivative of some constant would be 0. So once again, that's where that 11x to the 10th would come from. But this would be the process that we'd be going backwards, is we'd be adding 1 to the exponent and then dividing by it. Rather than multiplying to the front, then subtracting, it's that inverse order of what's going on. On number 14, they tell us g of x equals -4 cosine 4x. Okay, so we're told to find the antiderivative of this. So we're trying to find what the integral of this would be. So as we're looking at this, we're trying to figure out, well, what are we going back to? So some of the things that you got to remember, that we had the original derivative that we work within here. We can go back through formulas where we got to be thinking, okay, what gave us the derivative of what gave us cosine? So if we think about this, sine of 4x. Okay, so if we had sine of 4x and we took the derivative of sine would be cosine, and then we have a chain rule, so we'd multiply what's inside would give us the 4, and then we would leave what's inside would be that 4x. But we're missing this negative sign, so that negative sign never really came through. So once again, that negative was kind of out front in here. And then we got plus c. Now, I kind of worked through this one fast just because this is kind of one of those that hopefully you're able to start seeing and start realizing that if I take the derivative of sine 4x, that is 4 cosine 4x. Oh, wait, 4 cosine 4x, so that means the integral comes back to be sine 4x. The negative isn't accounted for, so we have to leave it as that multiplying scale factor that could have been factored out front or brought out front and then brought back into the answer. And then remember, we have to have that plus c, because once again, we don't know if we take the derivative of this, and we could derivative of that constant's at 0, so we don't know precisely what's going on. So please do not forget about the plus c. If we go to number 22. 22 says f of t, cap f t equals pi. So now if we're thinking about this, okay, this is really the integral of pi. I'm just going to go dx, okay? Now pi is a number. So if we think about it, this originally had, or this has a x variable here, but it's x to the 0 power, because x to the 0 power is 1. 1 times pi is pi. That's why it was just a pi here. So now if we add 1 to this exponent, okay, we see that we have x to that first power, and then we divide by that 1, so we have pi over 1. And then simplifying this is really pi x, and then once again in that n we have to add that plus c. So this is where that integral, or that indefinite integral, is taking us, and it's telling us to work with this. So let's look at a couple more complicated problems. Number 26. Number 26 talks about the integral. Move it up here for you. Of, here we have 5t over t squared plus 4t squared dx. I'm sorry, dt. Our variable's t in here, not x. So we got t as our variable. So now if we remember back properties of derivative, if we have a sum, we can do them separately and then add it. So we're going to do the same thing here. So I'm going to break this apart and kind of simplify an easier way to think about this as we go through. So we're going to take the integral of 5t to the -2 dt plus, we're going to take the integral of 4t squared dt. So if we add 1 to this exponent, that means we would have t to the negative 1 power. Now we divide by a negative 1, so 5 divided by a negative 1 would be a negative 5. Plus then, if we add 1 here, this would be t cubed. Divide by that 3 then would be 4/3. And then we would have that plus c. Now we really should clean up this negative exponent that we're looking at here. So we have negative 5 over t plus 4/3 t cubed plus c. And this is really how we should write this final answer in here. It's a little bit more clean as we work through this problem. Now if we look at number 30, number 30 starts bringing in our radicals. So if we look at number 30 here, it says that we want to take the integral of 6, and then we have the cubic root of x dx. Well, one of the easiest ways we work with these radicals was not as a separation, because then we had that whole chain rule. Then now we have to use the inverse of the chain rule, which we'll cover later in other examples, not so much today, more down the road. But we would write this as an exponent. So once again, we have a rational exponent. So now we look at this and we say, okay, add 1 to our exponent. So 1/3 plus 1 is 4/3. We're now going to divide by that, or basically multiply by the reciprocal. So we're going to multiply by 3/4 then. And then we're going to have, once again, our plus c, but I'll wait till I get my final answer to add that plus c in, because it always just gets lumped together with each of them, kind of like in that past one. You know, I technically could have had plus c for each of these, but if I add an arbitrary constant and add another arbitrary constant, I just get a third arbitrary constant that is relatively in here, so we just consider it to be lumped together. So considering what's happening here, we have 9/2 x to the 4/3 plus c. Now you could always double check these. At this point it's pretty easy to double check. 4/3 times 9/3, so 3 would cancel, 2 would cancel, oh, we'd be at 6. And then subtract 1 away, x to the 1/3 power, so that gets us back here. The derivative of a constant 0, so it eliminates every other part in there. So it's just one thing to always be looking at as we keep going through, to kind of double check what's going on. Looking at number 42. 42 is a trigonometric one. Okay, so here we have the integral of sine theta minus 1 over cosine squared theta. Now, if we start looking at this, we basically have a quotient thing going on where something was square. We have issues in here. But wait, we have a single part down here. So before we start performing our integral, I should add the d theta in here. Before we start evaluating this integral, let's break it up into a couple things that we know. So if we think about this, this is sine theta over cosine squared theta minus 1 over cosine squared theta d theta. Okay, so if we consider sine over cosine is tangent theta, and then once again this was a cosine squared, so this is really cosine theta times cosine theta. So if I take sine over 1 cosine theta, I'm left with 1 over cosine theta, but 1 over cosine theta was secant theta. And then we're going to say d theta, and then now we're going to subtract off the integral, once again looking here, of secant squared theta. Now this is where you have to go back to your table on page, let's quick look here, on page 322 they tell us those trigonometric ones. So if I look at tangent secant led back to secant. Okay, so it led back to secant on here. So this was secant theta. So the derivative of secant theta is tangent theta secant theta. If we come here and we look at that secant squared, then, wait, that was that minus tangent theta. Okay, And then once again plus c, because in the very end we have this whole arbitrary constant that we're adding to. And so this is what it really starts boiling down to. It starts boiling down into taking things backwards. And how do we work them? Now, problems can get more difficult, and we can work problems all day long on here. But these are just some examples of what some of the basics are telling us. Now let's look at an application problem. So I want to get a fresh sheet of paper here because this problem is rather in depth and is an excellent problem that you're going to want to reference for your homework. We're going to jump all the way over to 98. Okay, so 98 is kind of bringing that application in here. So they talk about considering the following description of the vertical motion of an object subject only to acceleration due to gravity. Okay, so they talk about acceleration due to gravity. A sub t equals the derivative of our velocity function, which talks about gravity. Okay, and once again, gravity equals negative 9.8 meters per second squared. Given this, it tells us to find the velocity of an object in relative times. Find the position. So they tell us that we have a stone is thrown upward with velocity. So a velocity of 30 meters per second from the edge of a cliff 200 meters above the river. Okay, so if we think about this, I'm just going to draw. So we got a cliff. Here we have our river down here. So this is our river. We talk about this as being 200 meters high, and you're up here. Perfect drawing of a stick figure, and you're going to throw this rock up. Okay, and we all know you're going to throw this rock up, also it's going to start coming back down in here. Okay, so you kick it in with this velocity right here. So it's asking us to figure out, well, what's going on with everything? What's happening here? Okay, so if we remember back, A of t equals negative 9.8. Okay, now it's going to ask us in part A. So part A, it asks us for what is the velocity of t. Okay, so the velocity of t is going to equal the integral of the acceleration formula. So if I take this negative 9.8, once again dt, because time is our variable in relationship here, we're going to take the integral of this. So what we get here now is we get that we have a negative 9.8 t. Once again, this was t to the 0, so I add 1, that's a 1, then divide over, we get this. And then plus c, so we see our velocity of t equals this. Now, we can't just go around here with this arbitrary constant, okay? We actually have to figure out what this constant would be. So what we would look at now is we would look at what was given to us, that we knew, or we know that the initial velocity was 300 meters per second. So what does that mean? That means that this velocity was 30 when time was 0. Okay, so we plug 0 in for time, we have a velocity equal to this. Now we're able to basically solve, and we see that negative 9.8 times 0 was 0, 0 plus c is c, so we get c equals 30. So if c equals 30, now we know our velocity function is negative 9.8 t plus 30. Then it asks us to find the position of an object for all relevant times. Okay, so now we want to go to that standard position formula. Okay, so once again, the standard position formula, well, the derivative of the standard position gave us velocity. So if we take the integral of our velocity formula, that negative 9.8 t plus 3 dt, we're going to take the integral of this. This is now going to give us that standard position formula overall. So we see here that we have s of t equals, okay, so we're going to add 1 to this. So if we add 1 here, that would be 2, so we have t squared. We then divide by 2, so we get negative 4.9 t squared. plus 30t, and then plus c. Once again, that arbitrary constant comes into play. Now, once again, like we did in velocity, we can't have this arbitrary constant. So we go back to the original problem, and we see that our initial height is 200 meters above the ground is where we're throwing this rock up, and it's going down then into that river. So we're seeing this. So now what we do is we plug in that 200 feet equals negative 4.9. Once again, the time at this was 0. Okay, sometimes we might know some other point in time where, 1 second into flight it was at so many feet. That's where then we would have to be plugging in those values here, that seconds, and then what the actual height would be here. So once again, 0 plus 0, so we get c equals 200. So we see that s of t equals negative 4.9 t squared plus 300t plus 200. So we have our standard position. So here's our standard position formula. Here is our velocity formula. Now in part C it says find the time when the object reaches its highest point, and then what is that height. Okay, so to figure out when it reaches its highest point is basically when that velocity is changing from a positive to a negative. So I'm going to come here and just kind of change colors. I'm going to work on the side right here so I can still see these formulas, because if we want this highest point, we want to know, hey, where is the maximum on this? We think about the maximum of this height, because remember, this is my height formula. I can go like this. This is my height formula. This is my velocity formula. This is my acceleration. Okay, so we have our velocity, our height. So we want to maximize this. So that would be the derivative, which is the velocity. So we look at this negative 9.8t plus 30. When does this equal 0? Okay, so we would subtract 30, divide by negative 9.8. So we'd see that t would equal 30 over 9.8, which is approximately 3.06 seconds. Okay, so that's when it's going to reach this. So then what we do is we come down here and we state, well, if we have negative 4.9 times 3.06 squared plus 30 times 3.06 plus 200, we put all this into our calculator, we type it out, and then we see that this equals 245.92 meters. So once again, we have our height and the time at which it happens. That's kind of relating back to what our past was. Then part D, it says find the time when the object strikes the ground. Okay, so we want to see when is this height going to strike the ground. So I'm just going to kind of describe this one. Once again, I'm not going to fully work this one out, but when the height reaches the ground, this means height is going to equal 0. Okay, so we want to know when height equals 0. So that means we're going to take this original function right here of our standard position, and we are going to set it equal to 0. Okay, so we then would go into that quadratic formula, in which then you would see x would equal, say I have the answers worked out, to 0 or 10.15 seconds is what we start looking at here. Basically, this is kind of what starts happening within here. No, it actually wouldn't be 0, sorry. It would be a negative 1, but we don't worry about our negative ones. We only worry about that positive one because we can't go back in time. It would be cool. Don't get me wrong. If I had the option to go back in time and redo things, I definitely would. But this is, we have to look forward into what's happening. So at 10.15 seconds is when this actually would hit that water or that ground at height 0. So this is kind of that application. Once again, this is just knowing a couple key pieces of information. Once again, we know a constant, the deceleration due to gravity. A lot of times we can measure initial velocity, initial height. There are other formulas out there, but how were those formulas developed? This is how they were developed. Okay, that they were gone through this way, and this is what was given. This is why things are the way they are. Do realize that every formula out there was generally developed, and a lot of those development of formulas did derive from calculus. Okay, calculus helped prove quite a bit of formulas within here on why they're working and how they're working.